For trigonometric functions, two very simple derivatives are that the derivative of the sine function is the cosine function, but the derivative of the cosine function is the negative version of the sine function. So this is really, really tricky. People get confused about this all the time. Sine derives to positive cosine, but cosine derives to negative sine. This is something you're going to have to learn how to keep up with. I personally keep up with it based on the fact that I always think that cosine's kind of like mean to sine. Like sine plays nicely, but cosine doesn't play nicely and kind of forces the negative. And you'll see that in more relations as you get along, that relationship kind of holds. But anyway, that's just how I memorize it. However you need to memorize it, that's up to you. However, to prove this, it's a little tricky. It's mostly an algebraic and trigonometric exercise. You're going to have to need to know three big pieces. The first one is that the limit as delta x approaches 0, sine of delta x over delta x is 1. That's proved by the squeeze theorem. The second one is a trigonometric identity, which is that sine of a plus b is sine a cos b plus cos a sine b. And this one falls into that Pythagorean identity, which is sine squared of x equals 1 minus cosine squared of x. So, knowing this, we can actually prove the derivative of sine is cosine. And we could do the same thing for cosine, but it would be very similar steps, and obviously we wouldn't have enough board here. But if you set up that limit, so you take the difference quotient here, what you'll do is you'll use this expansion to produce these pieces. So you'll have the sine cosine and the cosine sine. Then what we're going to do is we're going to do a little bit of algebra here, and we're going to say, all right, I'm going to take this middle piece and break it into its own limit. Remember that limits, if they exist, and so I'm kind of cheating a little bit because I'm making some assumptions about the limit existing, but it's okay, it works out. But I'm going to take this and set it up as its own limit here. That leaves these pieces to come over here. If I factor out a sine of x, I'm left with cosine of delta x minus 1 all over delta x. So I have this piece here. Now the next line, if I bring this down, I can pull the cosine out because this limit is in delta x. So cosine of x is actually a constant, so we can pull it out of the limit. That's that constant multiple rule for limits. So we can pull that out, so we're analyzing this. Now we know that this limit here tells us that that's going to drop down to here. So boom, boom, boom. But now we can go look over here. I have this piece. Now I'm going to multiply. This is a minus 1. I'm going to multiply by the plus 1 case on top and bottom. And the reason being is if I try direct substitution here, I get 1 minus 1 over 0. So I just get 0 over 0. So that's indeterminate. So I have to be a little more clever. But one of the big things that comes up a lot is this ability to use this trigonometric identity to kind of short circuit the situation. So by doing that, I end up with cosine squared delta x minus 1 on top by multiplying that out. That's a difference of squares. And then this is 1 minus, but I have that minus 1. So instead of getting sine squared x or delta x, I get negative sine squared delta x here. So again, we're still cosine's just cosine, just traveling through. Once I have that sine squared delta x, then I can break this into two limits multiplied together. I can take one of the sine delta x's and this delta x on bottom and put it here. So what's left over is negative sine x, sine delta x, cosine delta x plus 1. Well, again, that limit is 1. And by direct substitution, sine of x doesn't change because we're doing delta x here. Sine of 0 is 0. Cosine of 0 is 1. So I have something times 0 over 2. So this is 0. Multiplied by 1 is 0. Adding cosine of x. is cosine of x. So again, it's an algebraic, mostly trigonometric exercise. I challenge you to try to do the same thing for cosine. See if you can get this. You're going to use a sum identity, but you're not going to use the same one because you're going to have to do the cosine sum identity. But you're going to use pretty much the same techniques to produce a similar result.